My name is Matthew Ralston, and I'm going to talk about the accessibility challenges that we faced when developing web-based lab simulations at Ryerson University in the Zhong School of Continuing Education. So these web-based lab simulations were developed as part of an online certificate for occupational health and safety. And so specifically they're used in a course about learning how to use various devices to test workplaces for exposure to potentially hazardous levels of sound, light, and heat, as well as evaluating hearing thresholds for different types of hearing loss. So why build web-based lab simulations? So simulations of labs can be effective and engaging and allow us to reach an even wider audience. And in some ways, they can even exceed the limitations of in-person labs. So we chose to build web-based simulations as opposed to, say, apps that you could download on your phone and test around the house to ensure a consistent student experience with the material that's not dependent on the hardware that they have. And of course, the COVID-19 pandemic provided additional incentive to provide online learning that people can do from home. So what sort of accessibility challenges are involved in this? Well, when creating these simulations, we're creating highly interactive custom interfaces using some non-standard interface elements. And we need to ensure that they fully support keyboard navigation using standard buttons like Tab as well as the arrow key when needed. We need to ensure that they're fully compatible with screen readers. We need to allow for the disabling and enabling of any audio and animated elements. And we need to provide instructions via the screen reader for any non-standard interface elements. And we also need to provide guidance through the interface through tab order and focus order to help students complete the lab activity. And the final point is that we had to do this across 3 completely different interfaces that were developed to serve the purposes of the labs. So the first type of simulation is what we're calling a workplace simulation. So these depict a workplace such as an office, a garage, or a restaurant from an isometric perspective, and the place is divided up into a grid. So students take a virtual device and take readings for each grid cell, following lab instructions given by the instructor. So depending on the specific simulation, they could be measuring for sound pressure, light, temperature, or wind velocity. So the readings that the device takes and the grid coordinates are displayed on the screen, and the students record these manually as they're completing the lab. So the image in this slide shows one of those workplace simulations. It's an isometric view of a garage with the map divided up into a grid and a sound level meter over a car engine. And then on the left side, there's a readout showing the decibel level being read at that location, as well as the specific coordinates on the grid. So the accessibility challenges for the workplace simulation primarily revolve around navigation and output. So since the map is divided up into a rather large grid, it would be difficult to navigate simply by using Tab to go from one element to another. So we implemented navigation with the arrow keys. Because there are potentially dozens of these grid squares, it's important for the student to be aware of their location on the map. Also, as the readings can change when you exit and enter rooms, the students need to be aware of what room they're in on the map, and that gives context to why readings might change as you exit and enter a room. So in the video clip that I'm going to play, the grid coordinates are announced by the screen reader for each move of the device. And then in addition, when the device goes from one room to another, the room change is announced.
Column A. Row 4, Column A. Row 5, Column A. Row 6, Entered Tire Service Column A. Row 7, Entered Car Service Column A. Row 6.
So another challenge is to provide meaningful output from the device. And as the device is moved or sits idle, the readings displayed on the screen has some random variation and change every second. So this would be too noisy to output every change to an ARIA live region. So instead, the screen reader simply announces the range, and the student still has to infer what the correct value is. So in this video, the range of readings is read as the device gets closer to a sound source. The student still needs to calculate that actual reading based on the range.
Column A. Row 1. Reading 73.1. 2. 77.1 decibels. Column A. Column D. Column F. Row 3. Reading 74.8. 2. 78.8 decibels. Column G. Column H. Row 3. Reading 79.2. 2. 83.2 decibels.
You'll notice that the reading steadily got higher as it went closer and closer to the sound source in question. So the next type of simulation is focused specifically on the sound level meter and measuring sounds and how distance and angle to a sound source affect it. So in this simulation, we depict a noisy sound source like a car, jackhammer, or saw. And the student takes measurements at these specific points or hotspots around the car that are all different angles and distances from it. And once complete, the students download the results as an Excel file for which they do further analysis in the lab. And then they choose a different sound source and start over again. So in this image on this slide, there is a car with a series of hotspots around it to take measurements. And all those hotspots are at different angles and different distances. And a sound level meter is being shown to take a reading. So for the accessibility challenges for this lab, when taking the reading from the hotspot, a small amount of time passes to simulate the time that it would take to take the actual reading. And so instructions need to be given via the screen reader on how to take the reading, and feedback needs to be given when the reading is done. So in this little clip, the first hotspot is focused on, and then instructions are given on how to start the reading, and then the completion of the reading is announced via ARIA live tag, as well as announcing the total number of hotspots read and the remaining ones, so that a student has a sense of how much time it will take to complete the lab.
A 1 hotspot. Take a reading by holding the space bar. The reading starts. The reading is completed. 1 out of 15 hotspots completed.
Another challenge, accessibility challenge, is implementing keyboard navigation in a way that guides students through the lab. As students need to complete the readings for all the hotspots before they are allowed to download the results, the focus order of elements on the page guides them through selecting a sound source, completing all the readings, and taking them to the download button. So this video demonstrates the focus order of the lab, and it's sped up to show all the way through the beginning and completion of one sound source, and then choosing the next sound source.
Sound source list. Menu bar with 3 items. Car, table saw, jackhammer, a 1 hotspot. The reading starts. The reading is completed. B1 hotspot. The reading starts. The reading is completed. C5. The reading starts. The reading is completed. All hotspots complete. Download results. Sound source list. Car. Table saw. Button selected.
So as you see, the student simply presses tab to navigate all the way through, and it guides them through completion of the lab. So the final type of simulation that was developed is the audiometer simulation, which depicts a device called an audiometer, which is used to measure hearing thresholds. So students choose one of 4 test subjects. the sound channel, which left or right, and then use the on-screen dials to choose volume and frequency. So they then play a tone and wait for the subject to react. The image in this slide depicts the control panel for audiometer and a test subject who's raising their left arm in response to a tone. So similar to the previous simulation, one of the challenges is implementing keyboard navigation in a way that guides students through the lab using tab and focus order, as well as providing feedback and instruction for any non-standard interface elements. So when each interface element is changed, the change is outputted to the screen reader. So as opposed to reading the state of all the controls, we just read it as each control is changed. And so when the student navigates to non-standard elements, such as the dials, instructions are given by the screen reader on how to use them. So in this video, just the student chooses a test subject and then changes the settings, all of which are announced by the screen reader. So the focus order takes the student through each setting.
Test subjects. Subject A. Subject B. Subject C. Subject D. Selected. Name, Edward Bolton. Age, 18. Audiometer channel toggle, left channel, right channel, left channel. Volume control. Use arrow keys to change. 5 decibels, 10 decibels, 15 decibels, 20 decibels, 25 decibels. Frequency control, 150 Hz, 250 Hz. Play tone.
So the last challenge that I'll talk about is providing feedback. So when the subject responds to the tone with visual feedback, this needs to be announced by the screen reader as well. So in this video, the tester tries a set of volume and frequency, and the subject will respond to it, and the response will be read on the screen reader.
Play tone. Button not pressed. Volume, 45 decibels. Frequency control, 2000 Hz. Play tone. Pressed. Not pressed. Subject raised left arm.
So there's a bit of a delay on outputting the response of the subject to avoid any collision with the screen reader as it announces interaction with the interface elements. So that's it for the specific accessibility challenges that I wanted to talk about. So now I'm going to play a short demo of actually using the application.
Toggle zoom. Button not pressed. Toggle animation. Pressed. Not pressed. Toggle audio. Pressed. Not pressed. Open help. Return home. Toggle display details. Pressed. Not pressed. Image of an auto shop with several rooms. There are 3 sound sources in the auto shop. A car engine, a tire service station and a car wash. The auto shop is divided up into a grid. The horizontal axis is labeled A to P and the vertical axis is labeled 1 to 11. On each grid cell, a range of sound pressure levels can be measured. Press Tab to enter the grid, and use arrow keys to navigate. The grid cell location and range of readings will be read, as well as transitions from one room to another. Column A. Row 1. Reading 73.1. 2. 77.1 decibels. Column B. Row 1. Reading 73.1. 2. 77.1 decibels. Column B. Row 2. Reading 73.1. 2. 77.1 decibels. Column G. Row 3. Reading 76.5. 2. 80.5 decibels. Column H. Row 3. Reading 79.2. 2. 83.2 decibels. Column D. Row 6. Reading 73.4. 2. 77.4 decibels. Entered tire service. Column D. Row 7. Reading 80. 2. 84 decibels. Column D. Row 11. Reading 88.1. 2. 92.1 decibels. Column J. Row 11. Entered car wash. Column K. Row 11. Reading 73. 2. 77 decibels.
You can follow the links in this slide to see video demonstrations of the other simulations if you'd like. Thank you for your time and your consideration.